Hi, welcome to lecture 6.4, talking about work. So last time we started introducing some physics ideas. We were talking about density and mass and how we could use integrals to find masses of objects, especially when the density was not constant, right? We're going to see a really similar story here. So there's going to be a sort of fundamental physics idea, work being force times distance. That's going to be like a simple multiplication. But then if the force is going to vary and not be a constant force, we'll have an integral come in. So that's very similar to the story from last time. So let's just kind of recap what we mean by work, force, and distance. So work is just force times distance. It's just a measure of how much energy is spent when you apply a force over a distance. So let's just see the example right away. So if someone lifts a 20-pound weight 4 feet off the floor, how much work did they do? Well, the work is the force times the distance. How much force did they apply? They had to apply enough force to overcome the 20-pound weight. So they're applying this force of 20 pounds. Remember, the pounds was a force number. If I had said it was like a 20 kilogram weight, I'd have to write down that 20 kilograms times gravity, because that would be the force, right? But this is just supposed to be sort of simple. So it's 20 pounds times 4 feet. That's the distance they go. And so that's 80, right? And this is pounds times feet. And you might have heard of the unit foot pounds before. So that's a unit of work. So again, this is not meant to be super mysterious. Like, work is just the number you get when you multiply force times distance. The only thing really that's interesting is that people observed, right, that like if I double the distance, like you want to say if I double the distance, that's like twice as much work, right? If I move it 8 feet off the floor, it's even more, or something like that, right? Also, if you doubled the force, it would be double the work, right? If I was on Jupiter or something where gravity is 10 times as much, it would be 10 times as much work to lift the same mass object, right? So that's all that's going on, is it's just supposed to be a multiplication of the force times the distance. So something you can think about here in terms of the units, or like the just geometrically, right? If I imagine, this is just totally abstract. If I imagine, like I did a multiplication, right? So maybe I should imagine the distance, and maybe I should imagine the force as like two sides of a rectangle. And then if I multiply them, I get the area of this rectangle, and that area would be the work. Right? And so then this kind of makes sense with what I was just saying, right? If I double the distance but keep the force the same, that's twice the area, that's twice the work. And if I keep the distance the same but I like triple the force or something, that's also like triple the area, so triple the work. We'll come back to that rectangle when we start thinking about integrals. Okay, I kind of started saying this out loud a second ago, but just kind of to see an example with the units. Kilograms is different from pounds. Pounds already includes the force of gravity. So here in this problem, they lift a weight with a mass of 10 kilograms and 2 meters off the floor still. So the work is the force times the distance, as before. And the distance is still 2 meters. So force times 2 meters. But we got to think about the force more, right? All I told you was the mass. So I can't put 10 kilograms here, because that's not a force. That's a mass. But we know that the acceleration due to gravity, force is mass times acceleration. So the force that this weight, that we have to apply to this weight, is the mass times the acceleration due to gravity. So we just have to incorporate 98. We have to incorporate the gravity when we're calculating the work. So coming down here, our force now is 98. kilogram meters per second squared, and then we have times 2 meters. Okay. Yeah, and by the way, if we sort of combine the units like we've been doing, you would get newtons. Remember that was this part. Newtons times meters. So you may have heard this before as well. A Newton meter is a measure of work. So it's sort of a measure of energy, sort of. Okay, so that's work is force times distance, rectangles, multiplication. That's for when it's a constant, when both of these are constant, right? Constant force, constant distance. I apply one force over one distance, that's it. I might want to vary my force. I have a force that changes as you go. At the beginning, I apply a little bit of force, then at the end, I apply more force, something like that. So just like we saw with density, when the thing I'm applying is changing over time or changing over position, I can use an integral instead. The idea, sort of, is going to be like, let's say I apply, like with this rectangle idea, let's say, here's my force function. Let's say at the beginning I apply some amount of force, but then I suddenly apply a lot more force for a certain amount of time. And then I apply only a little bit of force. And then I apply a lot of force, right? The distance, the widths of these rectangles are the distance over which I'm applying these different forces. So I apply a medium force for distance 1, a bigger force for distance 1, a really small force for distance 1, and then maybe like a really big force for distance 3 or something. With this multiplication idea, I could find the areas of all these rectangles. That would be the work over each small chunk, and then I can add up all those works over the small chunks to get the total work. That's fine for if your force function changes like this, where it's flat, and then some other number but flat, and then some other number but flat, right? But we're interested in what if the force, like, varies continuously like this. Well, we've done this before. These rectangles will approximate this continuous version, and so we're just going to do an integral to get the area instead. And that's going to be the idea. So let's see in this example. Basically, you just have to know that work is the integral of force. So this is actually a common thing in physics. When something was a multiplication, when it was constant, it becomes an integral when it varies. So like we had mass was density times volume, but then we went to continuous, the mass was like the integral of the density. So here work is force times distance, but now it's the integral of the force. Okay, so let's just read this story. Suppose you're only a snowball over a distance of 10 meters, and I forgot to write this. I'm going to say with a constant acceleration. You need this, let's say 2 meters per second squared. As it rolls, it gathers snow, and its mass increases following some function. So the point of the snowball story is that this is a situation where the force actually will change over time. There's a different force that's happening to the snowball at different points in time because it's growing, right? At the beginning, it's a small snowball. The force comes from the mass, right? Small mass, small force. But near the end, it's a big snowball because it's gathered the snow. And since it's big mass, big force, so the force is different at the beginning than it is at the end. We can find the total work to roll the snowball, say 10 meters. So let's just see, we're being asked to find total work. It's the integral from A to B of the force. So I just have to figure out what A and B are and what the force is. It says roll the snowball 10 meters, so probably, I'm imagining, right, 0, 10, small snowball, bigger snowball, bigger snowball, bigger snowball, right? So at the beginning, that's 0, and then I move to position 10. So that makes sense. To figure out the force, well, we got to use newtons again, right? force is mass times acceleration, because we have the mass, and I gave you here the acceleration. Those two things together, we can find the force. So the total force here is the mass function, which you're just copying whatever that function was, times the acceleration, which I told you was 2. So that's going to be my integrand. And then I just do dx. So again, there's not a lot of math to do. Actually, writing it down is pretty straightforward. It's just about knowing the context. When they say work over a distance, that would be an integral, why that would make sense, and what integral exactly to write down. Something to notice here is that suppose like not doing the snowball, just doing like moving our rock from before or whatever. If we have a constant force, right? Say the force at every point in time was 3, right? Suppose the force is always 3. That's kind of like above, where we're lifting up the 3-pound rock. The force is always 3. So, and let's say the distance is 6 meters or something. I could still do my work, right? I could go from 0 to 6. I could do my force function, which is 3. That's the integral that I'm supposed to write down. But now look what happens. When I integrate this, I get 3t, or sorry, not 3t, 3x, right? It's supposed to go from 0 to 6. So when I plug that in, I'm going to have 3 times 6 minus 3 times 0. So look, we just multiplied, right? The result of doing the integral was just multiplication. So that's going to happen when you have a constant force function. The integral is going to essentially do multiplication. So here, you can think of this as the generalization of the regular multiplication with the rectangles that we did before. And if you think about this picture here, that should make a lot of sense. Imagine this was just a single flat line. Okay. Yeah, so that's just the basic idea. We can integrate force to find the work. A common application of this, which I want to talk about, is spring problems. So let's talk about springs for a second. By the way, springs might kind of seem random. Why are we talking about springs, of all things? In physics, springs, it's just like a really good, like, simple example. It's like a simple example that is still pretty simple, but is just complicated enough that it's you can have a little difficulty thinking about it. And so it's a good way to practice, like, thinking about physics stuff. Also, it turns out there's a lot of sort of physics things which can be modeled as springs or spring-like situations, even if it's not like literally a spring. So a lot of like particles and gravitational forces and stuff, like you can end up the situations where spring stuff sort of comes up, even if it's not literally a spring. But there's also a really good sort of toy example of physics stuff, like a pendulum or like a spinning disk or stuff like that. So let's think about springs a little bit. The main thing to know about springs is that they have an equilibrium position. So if my spring is just sitting there, not stretched or squished, it's just sitting there, it doesn't move, right? But I can also stretch out a spring. And the way I want to think about this is setting up a coordinate system where I'm marking, I imagine the spring attached to like the wall here, and then whatever its natural length is, right? When it's sitting at equilibrium, not moving, it's going to have some length, natural length they call it, and I'm going to label that position x equals 0. So when it's just sitting there, maybe it's 3 feet long, x equals 0 is the name of the right hand side of the spring. It's useful to have those coordinates because now if I stretch the spring, right, that means I'm pulling the tip of it out here to this position, which is some x position that's bigger than 0, right? And if I compress the string, I'm squishing it in to this position, which is some position x less than 0, some negative x position. The thing to know about springs is that if I squish the spring, it wants to go back to equilibrium, right? And if I pull the string out, if I stretch it, it also wants to go back to equilibrium, right? So when I squish it in, the spring sort of pushes back with a force that's in the opposite direction, right? I push it to the left. In my diagram here, left means squish. So I push it to the left, I feel the string pushing back at me to the right. And so what people noticed is that you can actually just write down force is K times X. So K is a number that you can just measure depending on the string. So it depends on the material, basically. So the thing about the formula is K times X. What this is saying is that if I, again, just like with the force from before, what's interesting is that the force is directly proportional to the X. If I push in 1 inch, I feel some force on the spring. But if I push in 2 inches, I feel a larger force, obviously, right? What people noticed, and Hook, I guess, I don't really know the story, but what Hook, I guess, noticed is that if I push 2 inches in, I feel exactly twice the force as if I push 1 inch in. Right? That's not obvious. Maybe if I push 1 inch in, maybe if I push twice as far, it pushes back like 4 times as hard, or something like that. There are some objects that do behave that way, right? But it turns out when you sit down and measure springs that if I push twice as hard, it pushes back twice as hard. Like, it matches exactly. That's sort of interesting. And same with pulling. If I pull it, it pulls back at me with the same force, as opposed to like square my force or double my force or something like that. It's the same force. And what's different between different springs is just what that stiffness proportion is, right? So if this K is like 2, then that tells me my force when I push, if I push 1 meter, I get 2 force coming out. Something I'll mention is sometimes you'll see, if you look online or in a book, you might see this written as negative kx. So it's just a matter of how you're setting up the coordinates here. What you want is to have the force, like if I'm stretching the spring, I want the force to be pulling left. So if I'm stretching the spring, the way I've set up these coordinates, x is positive. So I want to have a negative force. I want a force going left when I put in a positive number. So in that case, you would want to use this formula. But if you could also set up the axes the other way around. So there's different ways to do it. It's not that big of a deal, but just worth mentioning. Okay. So that's sort of just crash course on how springs work. Let's look at some specific problems where we're going to do integration, right? So here's where the integration comes in. If I'm pulling the spring, like in this problem, how much work is needed to compress the spring 0.5 meters from its equilibrium? So I'm imagining here's 0, that's equilibrium, and I'm squishing it down to negative 0.5 because I'm squishing it, I'm compressing it 0.5 to the left of equilibrium. So there's this motion that I'm doing, right? I'm going from position 0, I'm moving it over to position negative 0.5, and I'm going to track that as I'm starting at x position 0 and going to x position negative 0.5. We saw in the previous problem that to get work, I can integrate the force. So I have a force that's happening. What's the force? It's k times x. That's my law for springs. Whenever the springs, the force is k times x. So in here, we're actually told k is 100. Again, you can measure that. That's something you measure from the spring. So I write down 100 times x. That's the force that would apply at any moment along the spring. Along any part of my compression, I'm feeling that force. So my total work is integrating that force along my journey from 0 to negative 0.5. Okay, cool. So with this in mind, we can just do the integral, right? If you integrate it, you're going to get this. And then we're going to plug in our numbers. because of the squared here, whether you're moving left or right, you're always going to get a positive number out of this. You can double check that here you're going to get 50 over 4. And because they told us it was meters, we can say this is in Newton meters. Okay, cool. Yeah, so again, much like before, the setup is a little tricky. Like, you have to have an idea of how springs work. But the actual math you're supposed to do is pretty straightforward. Like, you just write this integral down. It's an easy integral, and you just do it. This is, part of the reason calculus was even invented. People were trying to do physics, and they were thinking about continuous force being applied and things like that, and wanted to imagine getting the total work. And the actual math is pretty easy. Okay, let's look at another example. So same spring, but now we're going to stretch the spring 0.25 from equilibrium. So again, I'm imagining here's equilibrium, then I'm stretching it up to position 0.25, right? I stretched it from position 0 out to position 0.25. That journey starts me at 0, sends me to positive 0.25, and I'm having this force act the whole time, and then you just do it. Same integral. Something that can be a little tricky with these spring problems is sometimes they have this kind of weird phrasing. How much additional work is required to stretch the spring 0.25 meters if it has already been stretched 0.1 meters from equilibrium? So let's just sketch here again. Here's equilibrium. It has already been stretched 0.1 meters from equilibrium. So I've already stretched it to here. But how much additional work? I'm going to further stretch it from here 2.5 meters more than what I'm already at, right? Stretch the string not to x position 0.25, but stretch it more, 0.25 more. So I'm going to go all the way up to, right after I do this, I have to do 0.1, that's where I was already, plus another 0.25. That's the final position I'm going to end up at. So that's 3.5. So I'm going to go all the way out here to 0.35. Right, so I don't care about the total work, like from here to here. I don't care about that. I'm interested in the additional work, so just going from here to here. I've already stretched it to 0.1. I want to further stretch it all the way to 0.35 and see what the total work is. As long as you figure out that that's what they're talking about, the math is really easy. You just, again, you go from the start to the end. So at the start of my journey, I'm already at 0.1, and then I go up to 0.35. And I plug in my force. And that's it. The thing to think about here is that, like the absolute x position matters, right? Even though I only stretched it, I stretched this 0.25 meters, that was the distance that I stretched over. But if I stretched it over that same distance, but starting from 0 instead, this would be a smaller number, right? You can check that by doing the math, but we can also think the graph of this function y equals 100x. It's just getting taller as you go to the right. So if I integrate over the same width but further along, that's going to be more area than the same width closer to the origin. This is reflecting that the spring, how hard it pulls depends on how far away from 0 you are. So in the first case, 0.1 to 0.35, I'm already further away. So at every moment, there's even more force than there would be at every moment in the right-hand scenario. There'd be some overlap, sure, but the total should be more. Okay, so that is springs. Yeah, so the last sort of topic I wanted to talk about in this physics section is lifting water. So again, this seems a little random, but it's pretty straightforward and sort of common to want to do this. So it's a good application. So let's just kind of think about it. So imagine we're trying to pump water out of a tank. I'm imagining a pipe. They don't usually draw this, but I'm imagining like a pipe sitting somewhere at the top of the tank or whatever. And I'm trying to pump all the water out. So what's the reason this is not obvious is that different parts of the water sort of have to move different amounts, right? If I imagine like scooping the water out like with a bucket or like pumping it from like a pump that's sitting on the surface or something like that, like the water that's in the very topmost layer, it only has to move a little bit to get out, right? The individual water particles sitting on the surface, like in this story, here's the water level is 8 and then the whole thing is 10 high. So these particles at the top, they have to move like 2 meters to get out. But the ones way down here at the bottom of the tank, right? Individual particle down here has to move 10 meters to get out, right? So the little chunks of water have to move more depending on where they started in the tank. So it's not just as simple as like multiply the weight of the water by 10 or something like that. There's this like varying amount of distance that a given slice of water has to move in order to leave. As we've seen a few times, if I have a varying quantity that I kind of want to add up the total, an integral is the right thing to do. Okay, so let's think a little bit more carefully about what I was just saying out loud. Even though different pieces of water have to move different amounts, what is true is that, like, try to think about this. Where would it be the same, right? Can you think of a group of water chunks that would all have to move the same distance to get out? Right, over the whole tank, there's different ones, but is there any group that kind of all moves the same? And something you might think about is thinking about slices, right? There's one sort of circular slice of water sitting at the very top. Maybe it's really thin. I bet all the particles in that sort of disk slice have to move, the same distance to get out. Or pretty much the same distance to get out, right? If I imagine a really thin disk, then the difference between how far the particles on the top of the disk have to move and the particles on the bottom of the disk have to move is not very much. Again, we're going to imagine taking a limit at some point, so it's okay if it's a little bit different at this level. You could also imagine like an infinitely thin slice of water, if that makes sense. All the particles in that slice, if there were any, would all move the same distance. What makes water particles different then is only what slice they're in, right? The particles in this slice have to move 2 to get out, but the water in this slice has to move more to get out, right? So we're just going to focus on one slice at a time. I'm going to imagine lifting this entire slice out and thinking about how much work it would take to lift that one slice out. I'm then going to basically add up all the slices with an integral. But let's think about one slice first. So what is this, right? It's a disk, right? Let's think about what properties, what like measurements of this disk we need, right? It's got a radius, right? It's got a height, and I'm going to call this little height here. Again, so I'm imagining a thin disk, but not an infinitely thin disk. It's a little sliver of height. I'm going to call that height delta x for some reason. Okay, so just say this right now, like we could probably think about the volume of this little thing, right? The volume of my disk, it's the area of that cross section, right? It's the area of this circle, pi r squared, times that height, delta x. Right, that's like a cylinder shape. The cross section area is pi r squared times the height, delta x. So just keep that in mind for a second. I'm going to say that this slice is sitting at a position named x, and we'll see why this is important in a minute, but I'm going to imagine putting some coordinates on here where I say, okay, let's have x equals 0 at the top and x equals 10 at the bottom. So I'm going to use this letter x to index which slice I'm at. I'm at slice, number 5 if I'm in the middle somewhere, slice number 2, right? This would be the top of the water because it only goes to 8 meters, right? Okay, so I have a slice at position X. What work does it take to move that slice out? Well, so let's say work for one slice. I know that the work is the force times the distance, right? I'll say force times distance. Okay, so let's think about this distance first. How far does this slice have to move? Well, I said it was at position X. Just think for a second. If it was at position 2, it would have to move 2 to get out, right? But if it was down here at position 10, it would have to move 10 to get out. So it seems like its X position, E, is the same number as the distance it has to move. And that's totally true. Right, to get to the top height, it's got to move this far, and X is another name for that line segment's length when I'm sitting here at position X. So here the distance is just X. By the way, we'll come back to this in a bit, but you can set up the axes the other way around. I could say X is 10 on the top and X is 0 on the bottom, and then that would affect my distance. It wouldn't just be X anymore. So maybe think about that, but we'll come back to that in a minute. Okay, so here, force times X. What's the force? Right, the force that is applied to this disk of water to move it out is the mass times the acceleration of gravity, right? That's kind of like we did earlier. Acceleration to gravity is just this number g. So it's 9.8, but you can just write g. I'm totally fine with that. What's the mass? Well, we saw earlier that mass is the same as volume times density, right? That's what mass is, volume times density. It's useful to break it up that way because I bet we know the volume of this disk. In fact, we did it already, right? The volume of the disk is pi r squared delta x. What's the density? It's the density of water. So it's how much water stuff there is per meter cubed, and the problem will always tell you what density of the liquid to use. We could just use rho just as a name for the number if you don't have a number to work with, but it's 1,000. The density of water is 1,000 kilograms per cubic meter, but you don't have to memorize that. Okay, and then just the last thing to notice here is what is R? Right? The main thing is, does R change as you go up, or does R stay the same as you go up, right? If I look at different disks. Because of the shape of this tank, R is actually constant the whole time. It's 4. We will see in another problem that the radius is not constant as you go up. But if it's a cylinder, the radius is constant as you go up. So we'll have pi times 4 squared is 16. Something else I'm going to do is I'm just going to bring the rho and the g out here, and I'm going to put the x right here. Remember, I can rearrange this, and I'm going to put the delta x out here just because I feel like it. Okay, so I know that's kind of a lot. We'll see in a second that there's not too much to remember. Like, you don't have to do this process every time. There's just like a formula you can write down, but I think it's useful to kind of go through that at least once and see where all the pieces are coming from. So yeah, let's do our total work now. We just computed the work that one slice takes to move one slice out, depending on its x position. The slice at position 2, I'd plug in 2 here. The slice at position 10, I'd plug in a 10 here, and that would be it. But if I want the total work, I want to integrate. I want to add up from slice 2, right? That's the the first water here, all the way up to slice 10, that's the bottom, how much work each of those slices takes, and I just write all this down. And now here's the trick. I'm not going to write delta x. I'm going to write dx. So I'm writing the delta x just to help you kind of remember that there's a thickness to the slice. But remember, the whole point of the integral is we're cutting it into a bunch of small slices and then making the slices smaller and smaller and smaller. So as the slices get smaller and smaller and smaller, you can kind of think of this delta x, which represents the real thickness of a slice. You can imagine it sort of becoming like this infinitely thinness of the slice. So we've talked about that before. So writing the delta x earlier was mostly just a like memory thing. The actual formula is going to be all this stuff, and then you don't have to, the dx will just be there because it's an integral. Okay, so that's the integral. I just want to kind of highlight what's going on here. So the bounds here is from the first slice to the last slice. And I'm saying first and last instead of top and bottom because you could set up your coordinates the other way around. Then you'd be going from 0 to 10. That's legit. You could do it that way too. But there's still like this would be the first slice, this would be the last slice. Whereas over here, this is the first slice and this is the last slice. So you're going from first slice to last slice. What are these pieces? Well, you're always going to have rho and g and dx. That's always going to be sitting there. This is the density of your liquid. It might not be water. Some problems have it be like oil or something. This is the acceleration to gravity. That's always going to be the same as long as you're on Earth. So that's just kind of always going to be there. Then the other pieces, right? What actually happened? We had this x, which came from just being the distance, right? So that's one piece you need, is what's the distance that the given slice has to move. And then what else? We had pi r squared times the height of my disk. This was the area of my disk, right? And this was the height of the disk. We said that the delta x sort of just becomes the dx, but we still had to figure out this area. So we're always going to have to find the area of the slice. So this really is the total work in pumping. Maybe a formula if you like, but it's more of like a template, right? The actual, like the first and last slice is usually easy. Rho g is always the same. The only math you really have to figure out is what's the area of my cross-section slice and what's the distance that a cross-section slice has to go. If you set up your coordinates the way we did with x is 0 on the top, then the distance is always just x. We'll see in the next example what happens if you do the coordinates the other way. The area is just the cross-sectional area of your shape. So here was a circle. There are some problems where it's like a rectangular cross-section, like you have a rectangular trough or something like that. In the next example, I think we also have a disk. But yeah, that's the basic setup. You have to figure out the area, you have to figure out the distance. That's pretty much the actual math you have to do, along with just kind of knowing what's going on and knowing what they're even talking about. So let's take a look at this example. Water tank is shaped like an inverted cone with a height of 6 meters and a base radius of 1.5 meters. The tank is full this time. How much work is required to pump the water out of the tank? So again, we already know what we have to do. I have to integrate area of one of my slices times the distance that a slice has to go times rho times g dx. And I got to go from the start to the end. So I just got to figure out what all these pieces are. I always recommend just starting with setting up the coordinates. So you get to pick them. Last time we did x equals 0 on the top. Here I'm going to have x equals 0 on the bottom just to show you how that goes. It's x equals 6 on the top because it's 6 meters tall. Let's imagine one slice sitting here. I need to know the area of that slice as a function of x, where x is representing, just a generic position between x is 0 and x is 6. I bet you can guess that this area is pi r squared, right? It's a circle. But I do have to think about r a little bit, right? Before, when we had a cylinder, the radius was constant the whole time. It was 4. Here, the radius is changing as you go along. So I need to think about, how does the radius change as we go, right? Here's the radius. If I had a bigger circle, the radius would be there. If I had a smaller circle, the radius would be there. So I can kind of imagine, this radius number as, a function of x, how high I am. There's a couple ways to do this. I'm going to show you two. So the first one I'm going to show you is just sort of directly taking this picture and just kind of turning it sideways. I'm going to have x down here instead, going from 0 up to 6. And I'm going to plot my radius. Right, the radius starts at 0, right? All the way down here, the radius is 0. And it goes up to 1.5, right? That's the biggest radius. And because it's a cone, it sure looks like this radius is just a straight line directly increasing as you go up. And you can assume that if they say it's a cone. Okay, so I just need to figure out what this curve is as a function of x. As long as I'm assuming it's a straight line, which is okay to assume, then I know it's a straight line. So I know it's mx plus b, right? Every straight line is mx plus b. I just got to figure out what b and m are. This line goes to the origin, right? R of 0 is 0. So that tells you about what b has to be. Right? No matter what the slope is, when you plug in 0, you get 0. M times 0 plus b has to be 0. And so b has to be 0. Right? When it goes to the origin, b is 0. So we know it's r of x is mx. We just have to figure out the slope. Well, what's the slope of this? Well, I can kind of think rise over run, right? It goes 1.5 high over the course of 6 across. So that's it. So r of x is 1.5 over 6x. That's the function for the radius. If you don't like the 1.5, we can make it times top and bottom by 2. That's 3/12, and that's 1/4. So r is 1/4 x. So sometimes you have to kind of go to the side and do this little bit of algebra to figure out what the radius function is. Let's look at another way to do it really quick. So this is sort of like the equation way. You can also think of it as sort of a geometry way. Here I have, let's just draw one radius. So that's like this one here maybe. I'm going to call that r because that's the radius, maybe as a function of x that I'm interested in. R of x, right? X itself is this line segment specifically, right? That's what I labeled here. This distance is x. So I can label this triangle x, this leg r. I bet I know the top leg of this right triangle is 1.5. And I bet I know the total distance here is 6. And I bet I also know that these are two right triangles that are nested inside each other. So you might remember from geometry that when you have two right triangles nested like this, you can say similar triangles, and you can write down ratios of the sides. So the way this works is I say, the one side to the one side is the same as the other one's one side to its analogous side. Right, so if I compare the short leg, 1.5, divided by the long leg, 6, of the big triangle, that's the same ratio as the short leg of the small triangle divided by the long leg of the small triangle. And there's a couple versions of this that you can write down. But if you rearrange this, you're going to get the same thing, 1.5 over 6 times x, or 1/4 x. Now, notice that that's really the same arithmetic that we did earlier to find the slope, right? We're just dividing 1.5 by 6. It's just whether you're thinking about it as sort of similar triangles or as like writing down a linear equation. Whichever one makes more sense to you. Okay, so one way or another, we get r, and since we're interested in the area as a function of x, I want r as a function of x, pi r squared. I just learned r was 1/4 x, so that's my r that I'm squaring, r squared. That's my area, so that's half of what I need. Okay, now let's talk about the distance. It's not just x this time. It's a little trickier. Let's just come back to our diagram and think about this. The slice here is sitting at position x, right? This distance is x. How far does that slice have to move to get out, right? It's got to move that far to get out. So however far that is, I'm just going to label that d. That's the distance I have to go. I don't know what it is yet, but I can call it d. Now, though, I bet we know something about d and x, right? D is the length of this upper segment, x is the length of the lower segment. Even if I pick a different slice, right? Pick this slice, I'll have a different x and a different d. But they still better add up to the same total, right? Because they're just breaking up that total height of 6 into two different chunks in different ways. So I get to write down the d plus x, right? That number better always be 6, the total height. But now I'm happy because I can solve, right? What's the distance that the slice at position x has to move? It's 6 minus x. Nice. So now we have our area function. We have our distance function. That's pretty much all we need to plug in to our integral. So the area is pi times 1/4 x squared. The distance function is 6 minus x. And then we have rho and g hanging out, and we have dx. The only last bit is what bounds do I put? The only reason to kind of think about this is that maybe it's not all the way full of water, right? I want to think what's the first slice and what's the last slice. In this previous example, it wasn't all the way full, right? The first slice was at 2, and the last slice was at 10. But in this example, it's full, right? They said it's full. And we set up our coordinates this way with x equals 0 at the bottom. So the first slice is happening down here at x equals 0, and the last slice is happening up here at x equals 6. So we'll have slice 0 up to slice 6. Cool. Yeah, so that's it. If you have real numbers for rho and g, you should plug them in to get like a number answer. But if I was just asking you to like set up the integral that would compute the work, this would be good enough. Usually it's not that bad of an integral because the pieces are just the area and the distance. So if the cross section is like a circle or a square or something, this area function is going to be simple. The distance function is always going to be x if the coordinates are as they were in the above problem, or it'll be something minus x if you flip them around like this. And so that's always pretty straightforward also. So the actual algebra here is never going to be too bad. Okay, yeah, so that is pumping, and just remember the main thing you have to find is what's the area function, what's the distance function. That's the only real hard part. Yeah, okay, so that's pumping problems. Yeah, these kind of just take some practice, so I'd look at some of the practice problems and just try them. But yeah, thanks for listening, and I'll see you next time.